All right. Shall we continue? Yes? Okay. First of all, before we continue, any thoughts on processing in memory? I promised that we would discuss if you have any thoughts at this point. Not yet? Should we have a discussion session sometime? I know you've been bringing a lot of ideas during the class, so hopefully class should be a discussion session as well, but should we have a session that's dedicated just for discussion and questions? What do you think? How many people would like that? How many people would not want that? Nobody raised their hand when, when I asked that question. But I didn't see strong support for it also. So maybe it's people are ambivalent. Do you prefer a lecture or a discussion session? Let me put it that way. Who says lecture? Okay, I see more hands right now. Who says discussion session? Okay. Okay, maybe we should schedule a discussion session sometime, but clearly there is not strong enough support. Interestingly. Okay, so let's continue the lecture. But feel free to participate in the lecture. If you have any questions, feel free to ask. Don't think that you would be interrupting me. That doesn't matter. If I cannot take your question at that point in time, I will defer it and we'll take it once the slide finishes or something like that, right? If you have any ideas, you should really talk about it if you have any questions. Okay? Like we've done in a lot of the previous lectures. Okay. So let's talk about low latency memory. I promised that we would be talking about multiple issues. We started with kind of architecture, the genomics, medicine and health. We talked about a lot of memory, security, reliability issues, row hammer. And then we talked about a lot of energy efficiency issues like memory-centric architectures. Today we're going to focus on low latency. And hopefully I motivated you enough for it earlier. But basically, the way I like thinking about it is we really want to solve some of the hardest problems that we have. And there are many, many hard problems that we have. This may be one of them, like modeling what's happening here. But there's a lot of hard problems. Climate, congestion. I actually give some talks that talk about some of those hard problems. I don't have the slides over here. But a lot of those problems are really, we want to cut down the latency to the solution. In the end, latency matters a lot. And if I have to deconstruct what I said so far over here, if you remember, for some reason Maslow's picture went away. There's an old version of the slide. Here's a nice picture where he's smiling at you. Just imagine, dream about it right now. But basically, all of these things potentially may be solved with speed, right? Maybe you don't really care about energy and reliability. In the end, if you have enough speed, you can navigate all sorts of security problems potentially, right? The bridge falling down, don't worry about it. I'm fast enough to avoid that fall off, right? It's possible, right? I don't know, I haven't proven it in computers yet, but I think it's possible to imagine this. So I think speed is a lot about latency in the end. It's also about bandwidth. We kind of talked about bandwidth, but latency is something that's really important. And I think this is also a property of a data-centric memory or memory-centric architecture. When I think of a data-centric architecture, these are some of the properties that we want. These are not necessarily comprehensive, I think, but they cover a good chunk. Clearly, we talked about the first property, process data where it resides, basically, or where it makes sense. And we talked about processing in and near memory structures to enable that, right? If you're data-centric, data is really what you really care about. And if data is what you really care about, you want to also enable low latency and low energy access to the data. I think of low latency from this perspective. It's really a property of a data-centric architecture. Also, you want to enable low-cost data storage and processing. I think this is also important. We will talk about some of these things over here. You don't want to waste storage, for example. That's why compression and techniques like that are going to be very important. Getting high capacity at low cost is going to be important. And scaling is all about that, actually, scalable memory. And I think intelligent data management is also important. And we've talked about this in various ways. And I think of these as properties of data-centric architectures. You want intelligent controls handling essentially everything. Robustness of data, security of data, minimizing the cost of data, maximizing the capacity of data that you can store. Today we're going to talk especially about low latency. we're not going to explicitly talk about low energy for some time, but a lot of low energy comes from low latency also, because if your latencies are high, you're really driving your interconnects for a really long time, and every nanosecond you drive, or every picosecond you drive your interconnect, you're consuming energy, basically. You can think of it that way. Reducing the latency is good for reducing energy as well, unless you're adding extra overhead to reduce that latency. And we will see some techniques where you're not adding extra overhead to reduce the latency. You're actually getting rid of the inefficiency, like slack in the system, to reduce the latency. So you will see that these are actually, these go hand in hand sometimes. Okay, so let's talk about this. So I will start with some fundamental trade-offs, and we will see as we discuss ideas some of those fundamental trade-offs. I've shown you this picture before. I'm not going to go through this in detail. But as we've seen, memory capacity has been improving a lot. Memory bandwidth also has been improving a lot, especially with 3D stack technologies. This increases even more. But memory latency has stayed constant for a really long time. And in fact, I present a graph that looks like this in 2013 in one of industry's big conferences called MEMCON. Memory conference, I guess, and I was an invited speaker, and the person who was after me, I think, was Bob Brennan from Samsung at the time. Samsung is the biggest company that designs memory, and he had a very similar graph showing that memory latency is constant, basically. In fact, his graph was less optimistic than my graph, I think. He didn't have the 30%. He said basically memory latency is flat for decades. We should do something about it. And he said one of the ideas that I'm going to talk about, this tiered latency Diem idea, is a promising idea to potentially reduce latencies. And we will get to it soon. In fact, memory latencies are constant overall, potentially, but some of them actually have been increasing. Like some of the latencies, if you go into dig into detail, this paper we're also going to talk about some of the internal latencies. For example, the pre-charge latency has been falling off, but then they've been increasing. Some of them have been increasing and have started decreasing. And the Samsung and Intel paper that we talked about on memory scaling, they predict that the write latencies are going to increase going into the future as we reduce the size of the cell because of basically slowness in the access transistor paths. So basically, with circuit or device level techniques, it's not easy to reduce latency at the cost levels that we're at. Basically, our goal will be to reduce the latency as much as possible without increasing the cost significantly. As we will see, there's a clear trade-off between latency and chip area. Chip area directly impacts your cost, and that's a very fundamental trade-off. The key question is, can we somehow circumvent that trade-off with creativity and new ideas so that we reduce the latency as much as possible while minimizing the cost? Okay, and I've shown you some of these pictures also before, but latency is critical for performance in these different applications. As I also mentioned, some of these applications are bottlenecked by a lot of different aspects of memory performance: bandwidth, latency, capacity. But latency is important. For example, when you have a query into a database, you really want that query to get fast from the user's perspective, right? Okay. And as I showed you in the previous part of this lecture, new DRAM types actually increase latency. Some of the new DRAM types significantly increase latency, and we will see this later on also. So let's talk about the memory latency problem in general. So latency increasing or decreasing, it doesn't matter. Latency in general is not very good. Basically, it's a significant limiter of system performance and energy efficiency. And if you look at the design of a processor, you really want to minimize the latencies as much as possible, right? If you look at ideas that we've discussed in digital circuits, for example, a lot of them are to reduce latency. And latency is becoming increasingly a bottleneck with higher memory contention, multi-core systems, and heterogeneous architecture. If you have many agents that are accessing memory, they collide with each other in the memory controller and they get delayed, so the latencies increase. So there are multiple parts of the latency. One is the raw latency to access DRAM. We're talking about main memory right now. Raw latency to access DRAM, main memory. And then there's also the queuing latency to access DRAM, right? And these are two different components. This raw latency, if it increases or if it doesn't reduce, and if you have many devices that are generating requests into DRAM, then you'll have contention, so that queuing latencies will increase. Right? And you need enough buffering in the memory controller. So both types of latencies are, certainly the queuing latencies are increasing, with more cores accessing memory. But the latency is also, the device latencies may also be increasing if the DRAM standards increase the latency. Right? And this exacerbates also the bandwidth need, because one of the ways of tolerating latency is accessing memory in parallel. That's also very fundamental. You can always try to tolerate latencies by increasing the parallelism. Right? If you have two memory channels, for example, then you reduce the contention problem. Different workloads can go to different channels, right? But also that comes at a cost, clearly, which means that exacerbates the bandwidth need. You cannot do with a single memory channel. If you want low latency, you need multiple memory channels, right? And you also need to be able to utilize the memory channels well, because if you have two memory channels and somehow your data is mapped to a single channel, especially the hot data that you're accessing, you're back to square one, right? Even though you paid a lot of cost to get multiple memory channels, you're not utilizing them well. And this is a real problem. If you remember the example that I gave you from Zürich airport, where you're partitioned into two when you're actually getting loaded into the train or the tram in the Zürich airport, if one channel is heavily loaded, the other part is useless, essentially. And that's what I experienced again in Zürich airport yesterday, actually. So this is the common case, I think I can call. And if your common case is that you've also already built these channels and you're wasting them, that's not a good place to be at. And this exacerbates the quality of service problem as well, because the applications that need low latency are getting delayed behind other applications that may or may not need low latency. Right? This is again the quality of service problem at the Zurich airport. You're getting crammed into this half of the tram and you're getting delayed because of that, whereas the other half of the tram is empty, but you cannot access it. Okay. On top of this, latency increases the processor design complexity, because you really want to, people figure out that they really want to reduce latency, and they design the processors actually to reduce latency. Modern processors are actually designed for latency. Modern memory is not designed for latency. I think that's another discrepancy in terms of the mindset that we have. Clearly modern processors actually incorporate a lot of mechanisms, which you will see in the next slide, to either reduce or tolerate the memory latency. Does that make sense? This actually, again, I haven't mentioned this explicitly this way, but if you look at processor design, it's very much latency oriented, whereas memory design is very much not latency oriented, as you can see in the trends. Even how the processors are marketed, right? People market processors in terms of frequency. They've been doing that for a really long time. And they kept improving frequency. Frequency is really about latency and bandwidth at the same time, of course. How fast you can, how much you can reduce one clock cycle. Okay, so it's actually a slide from my PhD proposal. These are some of the conventional latency tolerance techniques that are employed in modern processors, and there are quite a few of them. I think you can categorize the most prevalent ones into 4, and you're implementing one of them. You'll be implementing another one in another lab later on. But caching, and you can also see that caching, prefetching, multi-threading, and out-of-order execution. These are the 4 fundamental latency tolerance or hiding or reduction techniques from the processor's perspective. You can also see that they were initially proposed in 1960s. And they're widely used in existing systems. Caching, for example, it's simple, effective, but it's inefficient or passive. But caching reduces latency from the processor's perspective, right? If the processor has the data in the cache, it doesn't need to access memory, so the latency is reduced from the processor's perspective. This is what I mean by the processor is really designed for latency, because you have these huge caches. Whereas latency is still there, though, right? Latency is still there because the first time you need to cache the data, you actually need to go to memory, and that huge latency is there. From the memory side, the latency is not reduced. But clearly, these have upsides. That's why they've been employed. But they also have downsides. I didn't change the slide since 2003, by the way. It's the same. You can clearly, not all applications or phases exhibit temporal or spatial locality. If you have random access, for example, caching fails completely because you cannot predict what to cache. And increasingly, a lot of our applications are becoming more and more random access with the increasing data set sizes. Okay, prefetching. Again, prefetching reduces latency from the processor's perspective. It basically tries to predict which data is going to be accessed and fetches that data before the processor issues the load that requires that data. And clearly there was a lot of trade-offs associated with it, which we will talk about later on. It's employed in all processors that I know of today that are high performance. It's employed in a lot of accelerators also. For example, if you're building a machine learning accelerator, you should build a good prefetcher that can preload the data such that the data is there when the computation unit really needs to operate on the data. Otherwise, you will need to tolerate a lot of latency. Otherwise, you need to wait for the memory latency, basically. But prefetching works for regular memory access patterns. It becomes very difficult for irregular patterns. And once you have irregular patterns, actually this becomes very inefficient because you may actually get a lot of inaccuracy, and you actually issue prefetches that are wrong, and you actually waste bandwidth in the end. So you actually can reduce performance with prefetching. That's why usually modern prefetchers throttle themselves. They try to figure out how aggressive they should be, and if they're not doing a good job, they basically turn themselves off. Okay, multi-threading is a latency tolerance technique. Essentially, this doesn't reduce latency of an access, but it tolerates the latency by executing multiple threads, right? If you have memory latency in one thread, if you need to access memory, some other thread will be doing work. Right? So you can basically tolerate or reduce the cost of a single memory access. And this is also clearly important in GPUs where you can have multiple threads or many threads, and useful for applications where you can actually parallelize, right? But of course, this doesn't always work, right? What if you don't have multiple threads? It's a good question. If you're really latency bound, you really care about the latency of that thread, and you cannot parallelize that thing, then you're stuck. This doesn't help you at all. And people actually have tried to use multi-threading hardware to improve single-thread performance or reduce latencies in single thread. And this is not an easy task. If you have time, we may talk about that. And finally, out-of-order execution is a major technique that's employed again in, as we discussed last time, all high-performance processors, the restricted data flow. And this is very good for tolerating the latencies of things that are not cached and things that are irregular, right? If you can capture things with caching and prefetching, that's good. You may not need as much out-of-order execution, but where out-of-order execution is really beneficial is for those things that cannot be cached or prefetched very well. But it turns out this is also not easy to build, because as you increase the size of your instruction window, how many instructions that you can look ahead, execute out of order. Today we're on the order of 200s or so. Your processor becomes much more complex. You need to increase the size of all of your processor structures, register files, load store queues, reorder buffer, a bunch of different bookkeeping structures, and also clearly the restricted data flow engine, which figures out which instruction can be executed at this point in time based on data flow principles, right? Which instructions have their data ready at this point in time. So this is also not easy. This becomes more complex. This is also complex actually. If you want to tolerate more latency by adding more threads, you need to add more context into the machine, right? Register files, essentially different processor structures. Some of them may be shared, but you cannot share the register file actually as easily. That's why modern GPUs have lots of context, but a huge amount of register file space as well. Okay, any questions? All of these actually are subject of different lectures, but we're not going to cover everything. Okay, so if you look at all of these, they have one shortcoming. None of them really fundamentally reduce latency, memory latency. From the processor's perspective, they try to hide it and they try to tolerate it, but they don't reduce it. Okay, basically we're going to try to reduce latency. But I'm going to give you an example of these techniques because I cannot continue without doing so. I have to talk about my PhD thesis, which is run-ahead execution. I still think this is a very good idea, but this is a processor-centric perspective also. How can we make processors that experience less latency? And I'll give you the idea in one slide basically with a pictorial example. So from the processor's perspective, ideally this is what you want. Basically perfect caches. Your first level cache, ideally 1 cycle, or 0 cycle if you can make it, always sits. You compute and you get a load instruction and it hits in the cache, you keep computing without stalling at all. Right? That's what you really want. And the next load, it also hits in the cache and everything is good. What we get in real life today is, at least in the high performance processors, actually most processors today is this, they have small out of order instruction windows, which means that basically they compute, they get some cache miss because caches are not perfect, and while that cache miss is being serviced, they can execute some instructions out of order that come later, and they can overlap some of that latency of that cache miss. But at some point, their instruction window, how many instructions they can look ahead in the instruction stream, becomes full. And once the instruction window becomes full, you stall. That's the red part. You're not doing anything at that point. Maybe executing whatever is there in your instruction window at that point, right? But you're not fetching new instructions into the machine, which means that you're really not tolerating the latency of this cache miss. And then once the cache miss is done, it unblocks the instruction window, which means that you can now finish instructions and bring in new instructions into the machine so it can compute until the next cache miss. The next cache miss, and then the same thing happens, and then you stall for a long time, right? That's the idea. And from the processor perspective, ideally you would like to get rid of these stalls as much as possible because that's latency for you. So the idea in my thesis is run-ahead execution. It's a very simple idea. The realization is that we can do useful work during these stalls. Basically, when we get this long latency cache miss, we execute a little bit, and that cache miss soon becomes the oldest instruction in the window, because remember, we're processing an instruction window, and when you get the cache miss, it may not be the oldest one, but soon after it becomes the oldest one, because you retire or finish all of the older instructions. Hopefully they're not cache misses, clearly according to this picture. And that becomes the oldest one. At that point in time, you checkpoint the architectural state. You say, I'm going to save the registers, I'm going to save the program counter, and I'm going to go into a mode where I'm not going to stall. I'm going to bring in new instructions into the machine, and I'm going to execute those instructions speculatively. But the sole purpose of that execution is to discover new cache misses so that I can put them into my caches. And what am I going to do with this instruction that's at the oldest instruction? Well, I don't have the value of this load, clearly. So I'm going to assume that I don't have the value. I'm going to kick it out of the machine because I already checkpointed the state, right? That creates new space for new instructions that are coming in. They keep doing this during the speculative mode called run-ahead mode. You speculatively execute instructions, create space for new instructions. And hopefully, while you're doing that, you reach this load 2 that you couldn't have reached if you stopped. And if this load 2 is independent of the value that is missing, you could calculate its address and you could generate the miss that it's going to generate, and you could now start servicing this miss in parallel with this first miss. And at some point later, load 1 returns back from memory. The run-ahead execution engine identifies that and says, oh, I've executed ahead, so whatever I have in my machine is useless at this point, so I'm going to flush my pipeline and restart from load 1 because I've checkpointed the register file and the program counter. And once you restart, you re-execute some of the instructions you've executed over here, so that's the overhead. And at some point, while you're executing, the second miss completes. And when you really get to load 2 while you're re-executing, it hopefully hits in your cache because you've already prefetched it. And that means that you save a bunch of cycles. Right? That's the idea. So I think it's a nice idea. It's implemented in multiple processors. I'm going to show you a picture from Sun, their presentation. But this is a way of reducing latency or tolerating latency from the processor's perspective, right? What we're doing is we want to achieve low latency from the processor's perspective, so we actually pre-execute instructions speculatively so that we can parallelize these misses. And the latency of this miss is not exposed to the processor in the end, right? Although some of it is really exposed if you compare to the baseline, right? Clearly. Okay. Any thoughts? Yes.
So this is from the processor's perspective.
Exactly. Yeah.
What are the little like green blocks after like load 1 miss, load 2 miss?
You mean this one?
Yeah.
Oh, this is basically the processor can still continue computation because it has an out of order window where it can fetch and execute new instructions. Let's assume that you can your instruction window is 256 entries, which means that you can process. Whenever you have an instruction that's at the head of the instruction window, you can fetch 255 more instructions. So that's what it means.
Yeah, the instructions that it can do without having the data from the cache.
Exactly. Some of those instructions that you fetch are dependent on the data, but they wait basically inside your structures. Yeah. Exactly. So some of that data will need to be computed over here. Yeah, this is an abstract view of what's going on in the processor. Yeah. Okay. We may talk about run-ahead execution later on when we talk about prefetching, especially. But this is a method of prefetching, clearly. It's a relatively accurate method of prefetching because you're really executing the program to prefetch, and this can actually capture a lot of irregular cache misses that a prefetcher cannot capture. Because prefetchers are very good at capturing regular patterns. And this is really calculating what's going on in the program, right? Okay, so this sounds good, and these ideas are implemented in processors. This is an example from Sun's presentation on their ROC processor. Sun doesn't do processors anymore. They were bought by Oracle, and then I think Oracle doesn't do processors anymore as far as I know. They decided not to do processors very recently. But basically this was implemented in the ROC processor, and you can see that this is actually a nice study. They did it on online transaction processing workloads. They called this Scout, so whatever I called run ahead is called Scout, and their name is also nice, I think, because it's really scouting what's going to happen in the program. It's really bringing these cache misses into the cache before the program actually gets to that point. And they basically show that if you have a small cache size, you get significantly high performance, about 40% better performance. It's actually very much in line with the results that we had in our papers. And they also show that if you really want to get the effect of an 8 megabyte cache size, you could do it with run-ahead execution with 1 megabyte cache size. Basically, you have a small cache and add run-ahead execution on top of it. That gets you the effect of a large cache without run-ahead execution. So you could think of this as saving space as well. And if you're at this point in the curve, you could save even more space, as you can see. Okay, so these kind of latency-related ideas, and if you really want to know more, this is the first paper I've written. You can take a look at it. These kind of latency reduction ideas are there in processors. This is another paper. And if you want to make the idea work, you need to go into more detail. How to make it efficient is a key question, because while you're doing this processing, you're actually re-executing a lot of instructions. How do you actually reduce those effects? How do you actually try to get rid of the wrong path behavior? I'm not going to talk about that right now. But this idea and other ideas are implemented in real processors, as you can see. But none of them in the end fundamentally reduce the memory latency. So can we do better, basically? That's the key question. And that requires basically for us to understand what can we do better. And I think the realization should be that modern memory is really not designed for low latency, and as a result, we're adding all of these mechanisms into the systems to tolerate or reduce the latency as much as possible. And main focus, as you know, is cost per bit, capacity. And the second reason for latency and efficiency is modern DRAM latency is determined by the worst case conditions and worst case devices. We're going to look at both of these, basically. You could argue that this is a special case of the first one, actually, which is actually true. You could make an argument for that. But I'd like to treat them a little bit separately, because I think of this as more modern DRAM architecture is not designed for low latency. Here, where you add a lot of guard bands to enable the worst case conditions and worst case devices. Basically, if you think about the second one, because you really determine your latencies for worst case operation, like operation at 85 degrees Celsius, or operation to ensure that the device that is kind of weak in terms of latency is also acceptable, then you realize that much of memory latency is actually unnecessary. In the common case, let's say if you're operating at 50 degrees Celsius, latencies can be much lower, and we will see why. Because charge is much higher. You have a lot more charge in DRAM if you're operating at 50 degrees Celsius, which means that all of the access and sensing happens much faster. And if you know that you're operating at much lower temperatures, you can reduce your latency a lot. And we will see that from real devices. But we're going to look at both of these. So basically, the goal is really to reduce memory latency at the source of the problem, which is really where memory is. Right. Any questions so far? Yes? No? Okay. So it's a more data-centric point of view from that perspective, because processors already are doing a lot to reduce latency, but it's their perspective. It's the processor-centric perspective. Okay, so then the key question is, what caused the long memory latency? I'm going to repeat what I kind of said earlier with a little bit more precision, if you will. So there are two major reasons. Now there may be a third one that you come up with, I don't know. But let's look at the things that we know over here. The first one is the design of the DRAM microarchitecture is really not for lower latency. The goal, as we've discussed earlier, is to maximize capacity per area, cost per bit, not to minimize latency. The key question is, can we somehow redesign the DRAM microarchitecture to get the best of both worlds as much as possible. Minimize the latency as much as possible while not increasing the cost significantly. The second reason is we have one-size-fits-all approach to latency specification. Meaning, we use the same latency parameters across all temperatures, across all DRAM chips, that is part of a standard, across all parts of a DRAM chip, across all supply voltage levels, and across all application data. So can we somehow relax this? Basically, can we somehow use different latency parameters for all of these different conditions, as well as data? And the answer will be yes to all of them, basically. Of course, while you're doing that, you may reduce reliability. There are two key questions. How do you do it reliably, first of all, without reducing reliability, without getting errors in your application? And the next question is, if your application is tolerant of errors, can you push the latency reduction even more? Because maybe your application, maybe you get some bit flips by reducing the latencies, and we will see those bit flips in real devices. But maybe it's okay, right? Because your application, from your application point of view, it's another error in the data, and if your application is tolerant of data, like a lot of machine learning applications today are, as long as you don't increase your error rate significantly, you're still going to get similar accuracy from your machine learning while doing it much faster and much more efficiently. Make sense? And we're going to see an example of this in one of the later lectures, probably next week, with concrete machine learning workloads. Okay, of course there may be other things over here as well. So this is very much an area that's very open and active for research, and clearly industry is extremely interested in these directions. So if you have any other reasons over here, let me know. Maybe they'll become more clear. Okay, it's fascinating also because there's a lot of room for creativity. I also think of this as another example of mindset. People had the mindset for a really long time that we should not, they didn't explicitly say we should not reduce latency, but their mindset was we should improve capacity. Cost is a lot more important than latency, and that's the mindset. Once you challenge that mindset, you can come up with a lot of creative ideas, I think. That's true also, basically. Once you challenge the mindset, why do we have the same parameters for everything, or for all of these things, then you can come up with a lot of different ideas. And maybe there's something else over here, some other reason that should be challenged. Okay, so let's do a brief review of what goes on inside a DRAM chip, because some of the things that we're going to exploit are going to be inside. Oh, you've already seen a lot of this actually. I'm going to break this down in a different manner. These are slides that I used from my PhD student Vivek Seshadri. He did his PhD thesis. He's the one who developed the ideas of row clone and ambit, for example. He created these very nice slides also that I can use without thinking about them. I like those slides when I can use these slides without thinking at all. I'm sure you can use these also. But basically, this is a top-down view of the DRAM chip. This is a Diem. You can see inside there's a chip, and you can see inside that there's some structure to this chip. So we're going to look into that structure. And you can see there are clearly a lot of goals in designing the chip. Some of them are more important than others, cost especially. Latency is one of the lower ones actually. Reliability is one of the higher ones, but even there we're having problems, as you know. Power and energy, parallelism, bandwidth, all of those are goals. That's why DRAM chip design is actually not so easy. And this is true for a lot of memory chip designs. DRAM, flash memory, SRAM, whatever memory you have in your processors actually have similar trade-offs, except it's in a different context, right? Okay, so let's take a look at the DRAM chip inside. So if you look at a DRAM chip inside, we're going to look at some of the structures that we've kind of seen. This is of course pictorial, right? It's not necessarily representative of the exact DRAM chip. This is two kind of blown up, even though there are many of these internally. We just want to show two. This is a bank, and you can see that inside a bank you have two subarrays over here. And subarrays, you have an array of sense amplifiers, and this is the top part of the subarray and bottom part of the subarray, and this is another subarray with another sense amplifier, row buffer, top part and bottom part. And there's some I/O logic in the bank. Okay, and we've seen this also before. The sense amplifier over here, it really is an array or row of sense amplifiers, and this is a single sense amplifier. It's a cross-coupled inverter. You could use this as a data storage element also, right? The SRAM is like this actually. In an SRAM, static random access memory, this is really the storage element. And then you add two transistors over here to enable access to this, right? That's one type of SRAM. And those are the access transistors, very similar to what we've seen in Diem. But a sense amplifier is very similar to an SRAM cell, except it has some more things that I'm not going to discuss. Well, I'm not going to describe in detail, but I'm going to show. Basically, there's an enable signal that enables a sense amplifier. When a sense amplifier is enabled, basically it starts driving the bit line to the value that it senses. And there are two stable states that you have in a sense amplifier. If the sense amplifier is enabled, you can store a logical 1 like this. This is the bit line is 1. Or you could store a logical 0 like this. This is where the bit line is 0. We're assuming that this is the other side of the sense amplifier that's not connected to this bit line in the array. Okay. So, and also you've seen the operation of sense amplifier. Basically, it detects the perturbation in the bit line. If this is slightly higher than the baseline voltage over here, at that point, when you enable the sense amplifier, it starts amplifying and makes this VDD and makes this 0. You've seen this in the basic operation, right, for row clone and mbit. And basically, we're going to assume that this is logical 0 and logical 1. And okay, the key realization is that this is the Diem cell. Sorry, yeah, this is the Diem cell, and you've already seen this also. Basically, a Diem cell consists of a capacitor, and in the empty state, it stores a logical 0. If it's fully charged, it stores a logical 1. But clearly, you can encode these things differently, which we're not going to get into right now. But the key realization is that this thing is very small, and ideally, you would like to make it extremely small so that you can cram many more cells. And because it's small, it cannot really drive circuits. It can cause perturbation. It can cause charge sharing, but it cannot really drive the circuits. And the second thing is reading this destroys the state of it, as you also see. So basically, the capacitor is connected to the sense amplifier through the bit line, as we've seen. And when you access the capacitor, enable the word line over here, some perturbation is caused on the bit line, and the sense amplifier gets enabled after some point. And that enabling of the sense amplifier essentially amplifies the charge difference between this bit line and the other side of the sense amplifier. So initially, when everything is pre-charged, as you can see, as we discussed, 1.5 VDD, and the enabling of this word line causes a perturbation. That causes the sense amplifier to be enabled in turn, and once the sense amplifier is enabled, you drive the bit line either up or down, depending on the difference that you have between the two sides of the sense amplifier. Okay, everything is based on very simple circuit principles, right? Charge sharing principles. And once this, of course, is driven up, the capacitor gets filled also. It gets restored, in a sense. So whenever you're reading, you really destroy the charge in the capacitor. But soon after the sense amplifier is enabled, you're really restoring the charge in the capacitor, right? Okay, so let's build this up basically. If you look at a Diem subarray, this is a building block for a Diem chip. This is what I showed you over here. A single cell and a sense amplifier. Basically, we're going to have many more of these. This is a single bit line. And you see that the bit line is connected to many cells over here. In this case, we see 3 on the upper side and 3 on the bottom side. And this is where the other side of the sense amplifier is connected to. To make use of the sense amplifier well, you actually have cells on the other side also. Does that make sense? Okay, good. And this is running out of battery. Okay, and this is the array basically. This is a row, and you have many rows. That sounds good, right? And then you have a sense amplifier enable signal. And then you put a row decoder over here, and then you can decode which word line needs to be enabled. And this is the array of sense amplifiers, clearly. In Diem chips, different Diem chips, it differs, but at 8 kilobits is not uncommon. And then these are the different parts of the same subarray. So the subarray is divided into 2, the top part and the bottom part, depending on where the cells are connected with respect to the sense amplifiers. And now you can add more subarrays. Once you add more subarrays, you get a Diem bank. Right? In this case, you see a Diem bank with 2 subarrays over here, but in real life, you get like a lot more, hundreds essentially. And you get a bank I/O logic, which basically can drive data that comes out of the sense amplifiers. So sense amplifiers, let's say this is 8 kilobits over here, but the size of this is only 64 bits. As we discussed, again, if you want to read data out of the sense amplifier, read the column, we don't read the entire row, you really read a column. In this case, column is 64 bits. And why is it 64 bits? Because you really need to drive some data all the way across the bank, across many subarrays. Imagine hundreds of subarrays over here. And if you want to drive some data all the way across the banks, that's a very long interconnect, right? And that long interconnect needs to be very wide if you want to make it fast. And people try to make this one fast, relatively, even then it's slow because it's a very long interconnect. If you want to drive it fast, you need to make it wide. And if you want to make it wide, you cannot have 8,000 of them over here. So you basically have, let's say, 64 of them. Right? And you drive 64 bits out. So you can only read 64 bits at a given time out of this 8 kilobits whenever you issue a read command into the DRAM. Does that make sense? Okay. Okay, and then you supply the address, and that's how you activate the cell arrays. And you also supply the row address, and that gets also communicated over here, but it's not being showed. So essentially, that's what we have in the end. That's the memory channel. You can also, the next step is, of course, now your bank has 64 bits, but your memory channel may be even narrower than the bank. So your memory channel can be 8 bits, because these are actually now pins that are going out of the chip. Right? They're a lot more expensive. And even though you may have 64 bits out of your bank, you have 8 bits over here, you supply 8 bits at a time. And then you can burst the remaining 56 bits every cycle. Basically, every cycle you get 8 bits in this particular case. And the chip kind of looks like this inside nicely. Okay, so there's a shared internal bus between the banks, so only one bank can output data into the memory channel, as you can see. That's another limitation. You also get latencies. Even though you may actually access the banks in parallel, the memory controller needs to ensure that only one bank can load data onto this memory channel. So now you can see there are latencies accumulating, right, even inside a DRAM chip. Okay, let's look at the DRAM operation a little bit. We've seen a lot of these basically, but if you want to access this element, this column, let's say, inside that particular subarray, you first need to activate the row that contains the element, which brings the data into the sense amplifiers. And then the next step, you read or write to the column. Let's assume that you're doing a read, which means that you need to supply the column address, and the column address gets out from the bank I/O. And you need to prepare the array for the next access in the next step, which is a pre-charge operation, which closes the row and sets the sense amplifiers both ends to VDD over 2, right, to the reference voltage. So you've seen a lot of these, but we will see more of these in a little bit. Okay, you've seen a lot of the DRAM operation, but if you really want to look at the state-of-the-art DRAM operation, I would recommend looking at chapter 2 or section 2 of this paper. It's a chapter by itself, that's why it's section 2. But section 2 summarizes the DRAM operation from bottom up. Any questions? This was more of a background right now. And you've seen a lot of this, but this puts things together. So now let's try to answer this question. Basically, the first reason for the long memory latency is the design of DRAM microarchitecture. And I said that DRAM is designed to maximize cost per bit or capacity per area and not to minimize latency. And let's take a look at why that's the case. I'm going to talk about this idea called tiered latency DRAM. And we're going to ask the question, what caused the long latency? Now you've seen how internally this operates. And if you look at the cell array internally in a bank, it consists of a bunch of subarrays. Now we're going to abstract the DRAM latency as the subarray access latency plus some I/O access latency. And I'm going to posit that the subarray access latency is dominant because you can actually play a lot of tricks with the I/O access latency. You can do prefetching. In fact, as I showed you, internally you do some sort of prefetching, right? You bring in 64 bits, but the channel is only 8 bits wide. So you really prefetch 64 bits. And you can send those 8 bits every consecutive cycles. But the subarray access latency itself is really a full activate. And that's really much longer than how fast you can supply those 8-bit chunks out of the chip. That's why the subarray access latency is dominant. You can actually play even more tricks, I think, but I'm not going to talk about that. We'll see some more of those tricks later on. So the question is, why is the subarray so slow? Well, at least why is not fast enough? And if you look at the subarray, now we're going to abstract it this way, and this is a cell. The key realization is that you need to have a very large sense amplifier so that you can do all of those operations that we discussed, sensing and amplification. And the size of the sense amplifier is much larger than the size of a cell. And this is one of the DRAM manufacturers actually play a lot of tricks to fit everything in one subarray. And this large sense amplifier is not nice in terms of fitting things. Basically, if you want to maximize capacity, you really want to string together many of these cells in a single bit line. Right. In this case, you string together 512 cells, for example, but 1,000 cells, 1,024 cells is not uncommon also. What does this enable? This enables you to amortize the sense amplifier cost. If the sense amplifier is 100 times the size of a single cell, you're really amortizing that cost. This gives you the small area. But this also gives you a very large bitline capacitance, which means that it leads to high latency as well as high power. Right? Because now you have a lot of cells hanging off, and it's a very long interconnect. And whenever you think of latency, think of the latency of the interconnect. If your interconnect is long, your latency is going to be long. That's very fundamental. The distance, or latency, is proportional with the distance. Right? And this is the key trade-off. This is really the key trade-off in terms of latency versus area. Does that make sense? So basically, if you want to reduce latency, you may shorten those bit lines. In the best case, you will have only one single Diem cell in a bit line, right? And that is a very short interconnect, and the sense amplifier serves only that bit line. But now you need to have a sense amplifier for every single Diem cell. That's not good. If the size of the sense amplifier is huge, it's actually terrible. And that's the trade-off. Basically, we have a fundamental trade-off between area and latency. If you want to maximize area or minimize area, you really want long bit lines. But you can make this faster by doing what I suggested, by having shorter bit lines and having more sense amplifiers. And clearly in this picture, you've increased the area already, right? This is bigger than this one. And this picture doesn't even do justice to it. If you assume that the sense amplifier is much, much larger, this is going to be huge, right? But if you want to make things smaller, you should go to the left-hand side from your perspective. Right? You want to have long bit lines. So this is the area versus latency trade-off. Now let's take a look at this area versus latency trade-off with the real simulation. Yes?
Is not it because we are having the larger bit line, that's why the sense amplifier is bigger, because it will be able to drive there's a drop in the power. So we are using smaller bit line, so sense amplifier size should also reduce.
So that's true. There's certainly an effect in terms of how strong your sense amplifier should be and how large your sense amplifier should be. But that effect is more second order. Because if you make your cell extremely small, that perturbation still needs to be detected by a strong sense amplifier. And even if you have only one single cell connected to the sense amplifier, you really need to do a lot of work, and your sense amplifier still needs to be very big. But yes, you're right. If you string together thousands and thousands of it, your sense amplifier needs to be stronger and bigger as well. But I would argue that that's a second order effect. Okay, clearly we have a trade-off. Let's take a look at the implications of this trade-off. So this is what I'm plotting over here is latency on the x-axis and normalized Diem area on the y-axis. And these are for points for different number of cells in a bit line. And clearly, if you want to be cheaper, you go this way. If you want to be faster, you go this way. And ideally, you would like to be here, right? 0 for both. That's always what we want. So commodity Diem makes a trade-off on this end, basically. Commodity Diem is what you buy for cheap. And this is really what determines the Diem prices today. 512 cell per bit line, clearly, it's not fast, but it's cheap. Now you can buy some Diem in the field. I call them fancy Diem. There's reduced latency Diem, RL Diem, or fast cycling Diem, FC Diem. You can buy this. It's not manufactured as in mass as commodity Diem. So part of the reason it's expensive is not manufactured as much. Part of the reason it's expensive is because it has short bit lines. So you can reduce the latency, but at cost. And actually Diem manufacturers sell it for very expensive, very high prices. You can give your arm and leg to them if you want to buy these. And there are cases where these are used at for example, the backbone routers and internet, where you really need to make very quick decisions for routing. They use reduced latency Diem, and they pay the price for it because latency is extremely important over there. But you don't see reduced latency Diem in any commodity products that I know, any accelerator that I know of also. Right. Okay. Of course, you can be even lower latency as you climb this curve over here, right? So our goal is really to get here, and we don't want to climb this curve to get there clearly, and we want to somehow break this trade-off. And if somebody tells you they've broken the trade-off completely, let me know, because I'd really like to see that design. Usually it's a mistake, or they have a really creative idea that can break this trade-off. But I'm going to show you an idea that doesn't break the trade-off, but that enables you to have some flexibility, where part of your memory is here and part of your memory is here. Okay, and the idea is very simple basically. Whenever you see a picture that looks like this, you have a trade-off. This is small area, green, high latency, red. Short bit line, this is low latency, green, and large area, red. So you have complementary greens and reds. You can exploit heterogeneity, and heterogeneity is a very fundamental principle that we've discussed. And if you see a picture that looks like this, the first thing that could come to your mind is heterogeneity, right? And that's what we're going to do. We're going to start with a small area, substrate, long bit line, and we're going to introduce some heterogeneity into it that mimics this low latency area. And that's the idea. This is what it looks like. You have a subarray, long bit line, but you chop the bit line in the middle and enable isolated access to this fast area by adding some isolation transistors. Now, you get high capacity, clearly, and slightly higher area, because there's some overhead because of this, as you can see. But now you have control. You can say, I put my frequently accessed data to this part. This is called tiered latency Diem. As I said, you get small area using long bit lines, and this part can be low latency. Once you turn off the transistors, this part of the bit line doesn't get connected to the sense amplifiers, which means that sense amplifiers see a small bit line, which means that the data that you store over here can be accessed with low latency. But if you want to access some data that you did not store over here, that you stored over here, you turn on the isolation transistors, and the sense amplifiers see the latency of the full bit line in that case, but you can still access this part. Now the question, of course, becomes, what do you put over here, right? And you can use this as a cache, as we do in this work. Okay, so before we go into that, any questions? It's a simple idea, right? Whenever you see that green and red picture, heterogeneity should also come to your mind. But it's a simple idea in hindsight as well. Yes?
How it is different from directly storing the data in the rows near the sense amplifier?
So in the rows near the sense amplifier, this doesn't work as well, because your latency is still the entire bit line, because your charge is shared that way. But we will get back to that a little bit. Actually, then you need to use different timing parameters potentially. Right?
Because when we are designing any, when we are checking the latency, we check the worst case scenario.
Exactly.
If we see here, if we are able to allot the data which is near to the sense amplifier, then we can calculate the latency according to that. So it's a way to isolate it, but without isolation also we can.
Exactly. Yeah. No, your idea has merit, and we will get back to that when we talk about exploiting latency variation. In that sense, it's different. This is really changing the microarchitecture. So this could potentially be more robust, right? Because you clearly isolate this part. There is no noise that's coming from the other cells. But as you mentioned, you could treat this as a multiple latency substrate, and whenever you're accessing this row, you use smaller latency parameters. I think it will be less robust, but it's potentially doable. But we will see the caveats related to that later on. Okay. Now let's assume that we do this change to the architecture. What kind of benefits do we get in terms of latency reduction? This is activation latency. How long does it take to activate? Commodity DRAM is about 52 nanoseconds. And if you use a 32 entry, 32 rows in this low latency or near segment, and 480 rows over here, you basically reduce the near segment latency by 56%. This is actually wrong. This drawing, I had actually got it fixed, but I'm back to, I regressed to the wrong slide. So clearly this doesn't look like 56%, right? But it's really 56%. The bar itself is depicted wrong. It should be somewhere over here. But unfortunately, there's an effect. Your far segment latency increases now. Basically, because you introduce these isolation transistors, if you go back over here, once you turn on the isolation transistors, your bit line is kind of longer, first of all, but also there's additional resistance that you get, because when you turn on the isolation transistor, there is some resistance of the transistor, and the latency to access this part increases. So you have a trade-off, and that's a trade-off that you get with heterogeneous substrates. And if you look at power, the power actually is halved when you access the near segment, and when you access the far segment, it increases by 50%, as you can see. So it's another trade-off. So this substrate is very good if you're operating out of your near segment most of the time, right? That's what you would really like to do. And unfortunately, this comes at a Diem area overhead. It turns out these isolation transistors need to be relatively large, and the overall area overhead on Diem is about 3%, which is not bad compared to chopping off the bit lines and adding more sense amplifiers. Okay, so let's take a look at where we are. This is the picture that I showed you earlier. Our goal was this. Near segment actually breaks this period-optimal curve and takes us over here, right? You don't want to be at this point. Now actually you shift the point over here. Unfortunately, far segment puts us back, which means that we need to manage the substrate such that we're using the near segment as much as possible. Now this is an architectural substrate, just like row clone, so you need to take advantage of it, right? How do you take advantage of it? You can take advantage of it in hardware or software. There are many ideas that you can develop also. It's a sort of hybrid or heterogeneous memory within the same subarray. It's heterogeneous within the same subarray. There are many potential uses. You could use a near segment as hardware managed inclusive cache to the far segment. This means that you're really using that part as a cache, right? Which means that you're reducing your memory capacity overall, right? If you think of where you start, if it's 512, if you start with 512 rows per bit line, then if you used 32 of them as near segment, as an inclusive cache, this means that your capacity is 480 rows per subarray. This may or may not be good. Or you could use it as an exclusive cache, meaning that it's really part of your main memory, but whenever you're, let's say, moving a row from here to here, or whenever you want to store something into this cache area, you really want to swap it with something else in the other area. Right? This requires more bookkeeping. Inclusive cache is easier to bookkeep because you really want to keep track. You only need to keep track of what's in the cache. Here, it's really a mapping. You really need to keep track of what's where in the subarray. Right? That's why this is a little bit more complicated, but this can buy actually more performance because it's really not getting rid of the capacity that you have. What else can you do? You could use profile-based mapping from the operating system. Operating system can somehow figure out what are the frequently used pages. It can map those frequently used pages to this low latency part of memory. This requires clearly now more software support. Operating system needs to be aware of subarrays. It needs to be aware of the near segment, far segment in each subarray. But this is also possible. I think it's not a bad way of thinking about it also. If you can do it, if you can possibly do it. And the last one is this, basically. Simply replace DRAM with TLDRAM. Change the timing parameters accordingly, your memory controller, of course, so that whenever you're accessing near segment, you access with lower latency. But you don't do anything special to map data to this near segment. Right? So somehow the data is already mapped to near segment versus far segment, and you're really trying to take advantage of it. It turns out this doesn't work really well. This doesn't buy you any performance, because if you have a substrate like this, near segment fast segment slow, far segment slow, you really want your frequently accessed data in your near segment. It so happens that it doesn't happen that frequently accessed pages magically end up being in the near segment if you don't do anything special about it. Basically, you need to manage a substrate like this. That's the takeaway. And the paper talks about it also. So, but these three use cases actually provide performance improvements. I'm going to give you some examples. Any thoughts? Any other use cases that people can imagine? Clearly, if the programmer knows which part of their data is accessed a lot more frequently, they could use this. But I would also like to mention that this is a different kind of caching that's happening. This is not a cache that's in the processor. The processor cache you're designing in your lab, it's an L1 cache. It gets exposed to all locality. Now the L2 cache gets exposed to a different sort of locality. because the locality that you exploit in L1 cache is now filtered out, right? Now L2 cache, you have some other part of your working set and some different type of locality. It doesn't even see the accesses that hit in L1. L3 cache gets exposed to a different sort of locality. Accesses in L1, accesses that hit in L1 and L2 get filtered out. This is a cache on the DRAM side now. You basically have filtered out a lot of the accesses. L1, L2, L3, L4. All of them filter out. So what you really have is just memory accesses, main memory accesses. That's one difference. You have a lot of filtering that happened already in the memory hierarchy, assuming you use this as part of a traditional processor-centric system. The other difference is also very fundamental, I think. If you look at the cache hierarchy, you don't normally cache 8 kilobytes. Let's assume that your full row size is 8 kilobytes. You don't normally cache 8 kilobytes of data, right? You cache 64 bytes. Now, there's another benefit that you get in the basically what you're doing is caching at the row granularity in this case. And that's a different kinds of locality that you're exploiting. Clearly, you're exploiting spatial locality. And you may access this 64 bytes in the row. That may already be in your L1 cache. Now, if you access another 64 bytes, this is what is being sped up over here. If it's already in your row buffer, it's not going to speed up your access. It's going to speed up your access if this row that you're trying to access, if this other 64 byte that you're trying to access in this row, and that row is not already in the row buffer, right? Because row buffer access is very fast, as we discussed, right? So for this to work, you really need to be activating a row, and we want to try to reduce that activation latency. So imagine, when does that happen? When do you need to activate the same row again, and it's not in the row buffer? Any guesses? You want to activate the same row again, clearly, to benefit from this, and it's not in the row buffer. Remember, someone should have kicked it out of the row buffer, probably, right? Which means that you must have had a bank conflict. So basically, this works in cases where the same bank you're trying to access, and the first access is to row A, the second access is row B. Let's assume that you're ping-ponging. That's the worst case, of course. A, B, A, B, A, B, A, B, A, B, A, B, A, B. Instead of paying the full penalty of full activate across the entire subarray, you're really paying, by caching AB in the near segment, you're really paying, let's say, half the penalty of an activate, because we reduced the access latency by 56%, right? So the caching that happens in memory has a very different implication. First of all, you're really not benefiting from temporal locality, I will say, because temporal locality should hopefully have been filtered out by all of those caches that you have. You're really exploiting spatial locality on a row basis. It's also the spatial locality that should not be exploited already by the row buffer, right? Because if you're accessing only a single row in a single bank, that row should already be in the row buffer, and this should not provide you any benefit. So you can think of these techniques of caching at the DRAM level as ways of getting rid of or minimizing the bank conflict latency penalty. And bank conflict latency penalty is significant. If you remember the pictures that I showed you, a single DRAM device has 8 banks. 8 banks is not a lot. If you have, let's say, 100 processors, accelerators accessing 8 banks, you're bound to have some bank conflicts, right? That's the idea. Make sense? Okay, good. Okay, so let me give you some results with the simplest thing that we do, which is basically using the near segment as an inclusive cache. We want to get rid of, we're not even considering capacity over here. Basically, you can think of it this way. You have a subarray, you divide into the row buffer, far segment, and near segment. And far segment is your main memory, near segment is your cache. And row buffer is clearly a much faster cache, because you don't even need to activate it, right? It's already activated. Okay, so there are multiple questions over here. The paper talks about them, but I'm not going to go into detail. First of all, how do you efficiently migrate a row between the segments? Basically, we're going to use something very similar to row clone in this case, and you already know the idea. I'm going to animate it very quickly. Basically, whenever you access your main memory, how do you bring the row into near segment? You do row clone, right? That's the idea. The second question is, how do you efficiently manage the cache? Basically, what do you cache over here? Clearly, you can use many caching policies, some of which you're implementing at a different level of caching. Some of them may apply over here, some of them may not apply. I'm not going to talk about that, but basically we're going to have a fully associative cache, 32 entry or whatever number of entries over here, and we're going to use LRU, least recently used replacement, which is not necessarily the right policy if you think about it, right? Do you actually really have least recently used kind of reuse over here? Maybe you should do something else, right? Especially if you have multiple different applications sharing the cache over here, which we will talk about later on. I think the caching principles are the same everywhere, regardless of wherever you have a cache. But if the contention in the cache is much higher, especially from different applications, your reuse behavior also gets very different, right? Because now different applications will be contending for this near segment, and least recently used may not be the best policy. Because one application may be streaming through the cache, another application may be having random access, another application may have extremely good locality in the cache. You really want that application that benefits from the cache to use the cache, because random access you're not going to do much about. Streaming, hopefully you can handle with prefetching in some way, right? Okay, keep these in mind. So these results use perhaps the easiest policy. Okay, how do you migrate a row? Basically, this is row clone. I'm going to, actually this paper was published before row clone, so it proposes a way of cloning rows. But you activate the source row, which brings data into sense amplifiers, and then you activate the destination row. That's essentially row clone, right? And you get low latency activates. Clearly, you don't want to do this migration to the memory controller, because if you do it through the memory controller, you're basically wasting a lot of bandwidth. That's why you have to do something like row clone to take advantage of this. Okay. Let me actually qualify that a little bit. If you're using this as a dynamic migration substrate, where you dynamically determine which row needs to be put into your near segment, then you don't want to do it through the memory controller. But if you're doing it statically, like the operating system or somebody else maps the data statically, somehow they magically figure out that data that is accessed frequently goes here, then you don't need to do any migration. And if you can do that well, then it's possible to use a substrate without any row clone support, right? But I don't think that's a very general substrate. There are not that many cases where you can statically determine what should go into the near segment, especially when you're in a shared environment where many applications are potentially running at the same time. Okay, so how do you efficiently manage the cache? I already talked about this. Let me give you some results. These are results from the paper. Basically, performance improvements are reasonably significant. It's more than 10%. It's not like the processing and memory improvements. Don't expect those by changing the traditional architectures this way. But I think these are promising because this is using the very simple caching policy also. And these are averaged across, I believe, 80 workloads. This is DRAM power. And the DRAM power reduction is also significant. You can see that there's a significant reduction in DRAM power. And this is consistent across multiple cores and multiple channels, as you can see. And so the takeaway is basically using this as a simple cache with very simple policies still improves performance. I believe there's a lot more room for improvement by improving the techniques for caching. In fact, I believe that there needs to be more research into how to do the caching correctly on the memory side. There's a lot of research on how to do the caching well on the processor side, but there's very little research from the data-centric or memory-centric perspective. I don't believe that we know how to do the caching correctly on the memory side itself. If you're looking for research topics, this could be a good one. And by the way, caching is a fascinating area. People have been doing caching and writing caching papers for decades and decades, and there's no end to it. It's very important. It's very fundamental. And the International Symposium on Computer Architecture, it's called ISCA. People used to joke about it, saying this is the International Symposium on Cache Architecture. So what you're doing in your lab is very important in the end, and people spend a lot of time optimizing the caches. Okay, so there's also other trade-offs that you can explore if you have a substrate like this. The question is, for example, how long should your near segment be? And this gives an empirical result, and this is also based on simulation, by the way, a version of Ramulator, the C# version of Ramulator. Dong Kyok, one of my PhD students, implemented this over there. This was part of his PhD thesis. And you can see that as you basically there's a trade-off. As you increase the size of the near segment or length of the near segment, you get larger cache capacity, but you also get higher cache access latency. There's of course another trade-off that's not really depicted over here, which is you lose memory capacity if you use it as an inclusive cache. But that's not evaluated over here. We assume the memory capacity is large enough so that you don't get into page faults. Because once you get into page faults, if the trade-off is reducing the activation latency by 50% versus increasing your page fault rate, I would not reduce my latency by 50%. Right? You don't want to increase your page fault rate. You should be very careful in those cases. That's why you don't want to increase your memory capacity or use these only in cases where you know that your memory capacity is enough. Right? Okay, so you can see that the trade-off is, there's a peak of the curve over here at 32 cells, but even a single row in the near segment actually provides significant performance improvements. Why? Because you're actually reducing the bank conflict latencies this way. So even a single row provides you some freedom to reduce the bank conflict latencies. If you're doing AB, 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 AB in the same bank for different rows, you can cache one of them this way. Right? And you can reduce its latency. So that's the idea. Okay. And if you're interested, there's more in this paper. Any questions? Thoughts? Is that something what I did? Or somebody has a question or thought? Oh, you're trying to press?
No, maybe it's me.
Okay.
Oh, yes.
Yeah, go ahead.
No.
Oh, you don't want to ask, you just want to play with that thing. Does it work really?
Yes.
Oh, okay.
Hello.
Wow. Now you have to ask a question. Okay. Okay, any thoughts? Yes, you have to.
About refreshes, because I guess the rows in the far segment here will still be refreshed. Does that take longer time now?
That's a great question, and the answer is yes. Because refresh is fundamentally an activate and pre-charge, and that's what's happening, and those take a longer time. But correspondingly, the rows in the lower end take shorter to refresh. That's good. You're thinking about all of these interactions. And yes.
Would it be better if you use multi-level caching, like instead of having just the nearest or multi-levels?
Oh, basically, if you have near segment, next near segment, next near segment. Yeah, so that's something we did not evaluate, but certainly the idea is generalizable, right? You can add another isolation transistor at the higher part, and you can enable one of them and disable one of them, and that'll still be lower latency than the previous one. So I think it will provide a more graceful fall off of latencies clearly, but now you need to manage that substrate again, right? So the management complexity increases. What do you put into which level?
Also the area.
Also the area overhead increases, yes, clearly. But the paper doesn't really evaluate that. Although there's a discussion very briefly, I think, somewhere, and we've considered it, but dismissed it relatively quickly. Yes?
What's a page fault?
Oh, what's a page fault? Yeah. This is basically your physical memory is not enough to house all of your data. So you need to go to a disk to bring the data. If you're interested in learning more, watch my virtual memory lecture from Digital Circuits. We talk about it a little bit more. And that takes a long time, clearly, because now you actually need to bring the data from the disk into the physical memory, and that takes basically on the order of well, if your disk is an SSD, it's microseconds, right? If your disk is a hard disk, it's milliseconds. And clearly you don't want to cause page faults by reducing the physical space of your physical memory by doing this. That's why I think using this as an exclusive cache is a better idea, but it leads to higher performance overheads. It leads to higher complexity. And the paper talks about that use case also. If you're interested, you can take a look at that. Any other questions? This is your chance. Because I'm not going to continue, I think. We have only 10 more minutes. We're going to pick up from this point tomorrow. Going once, twice. I won't go the third time. Okay, I'll see you tomorrow.